So our function is going to be the square root of x, or whatever the thing is without the number here, right? We're just kind of replacing the number with x. And then our a value is going to be the value that is close to the number that we're trying to approximate this function at, that is easy to evaluate. In this case, it's going to be what? What's close to 38 that's easy to take the square root of? Yeah, 36. Okay. And then we also need the derivative. The derivative of the square root of x is 1/2 x to the minus 1/2, or if you prefer, 1/2 square root of x. All right. So then we need the equation of the tangent line, which you can either write as, yeah, I mean, you can write it a couple ways. You can say, y minus y1 equals the slope times x minus x1. Or y equal to y1 plus m times x minus x1. Or the linearization equals the y1 value, which is f of a, plus the slope, which is f prime of a, times x minus the x value, which is a. Right, there's your linearization formula one more time. Again, just the equation of the tangent line. Our f of a is the square root of 36, which is 6. Our f prime of a, which is our slope, is 1/2 root 36, which is 1/2 times 6, which is 1/12. So our linearization is 6 plus 1/12 times x minus 6. That's the equation of the tangent line. And our approximation here, so if we're trying to approximate the square root of 38, it's going to be approximately the linearization at 38, which we're just going to plug in 38. I've made this mistake twice now, and I apologize for it both times. I made an error here. In fact, actually, let me carry it out before, let me carry through the problem before anyone tells me what the error is. Hopefully you guys can see what error I made. So I'm going to get 6 plus 1/12 times 38 minus 6. And then if I do this, I get 6 plus 1/12 times 32. 6 plus 32/12 is kind of too big to be the square root of 38. 32/12 is almost 3. I'm getting close to 6 plus 3, which is 9, which is like the square root of 81. Clearly, I made an error. And the error is the error I made before, which is plugging in the wrong thing for a here. A isn't 6. I even wrote it down. A is 36. So really, this should be 36. And it should become obvious that we made a mistake, not when we get to the end here, but at this point right here. These two numbers should be relatively close to each other. This should be a small difference, because otherwise you're using a value that's really kind of far away. So really this should have been 38 minus 36. And then we're going to get 6 plus 1/12 times 2, which is 6 plus 1/6. Or if you prefer, 37/6. Well, I guess you could write it as a decimal, as 6.1666666, whatever. So this is an approximation of the square root of 38. If you look at a calculator, you will see that they're pretty close to each other. Let me also show you this picture, and I know we've seen this picture already, but let me show you this picture that's already drawn, just so I don't have to try and draw it poorly for you. Yeah. So yeah, here we go. Sorry, So this is the problem I was doing. We're doing the linear approximation of the root 38. And here's the square root function, as usual. And here's the tangent line at the point a f of a, which is 36, 6. And the difference in the x's is your dx thing, it's 2. And then here's what we're looking at. The dy is the approximation of the difference in the y values when you plug in 38. Right? Really, the actual difference, which I guess I can't really draw on this. I would like to draw on this, right? Can't draw on it. The actual difference, I lost my pointer though. Yeah, the pointer's better. The actual difference is from here to here, but we're using the distance from here to up here to approximate that difference. So we're doing f of a, which is the square root of 36, which is 6, plus the approximated difference, which is your dy. And your dy is just your dx, your run, which is 2, times your slope, which is 1/12, right? Because rise over run is slope. So the rise is just the run. Sorry, let me write this down so I don't actually say it dumbly. Whoops, let me stop sharing now. It's okay, I'm fine. My chair just hit the thing here. Right? Rise over run is your slope. So the rise, which is what we're approximating, is your run times your slope. Or if you prefer, your dy is your dx times your slope, which is your f prime of x. It's another way of thinking about it. So we're using dy, which is this part here, to approximate your delta y, the actual change in the function value. Sorry. I actually did hit my toe that time. That's what I get for fooling around, for pretending like I hit myself earlier. I really did hit my toe. It actually one sec. Okay. So let's look at one more linear approximation. Oh yeah. I don't remember. Did we do a trig one last time? We had degrees. Yeah, that's what I thought. So I want to make sure. Let's do a couple more that aren't that, and then we will do a couple other things. So let's say I want to approximate 1.95 to the 4th power. Same idea. I know that my function, f of x, is going to be x to the 4th, which I can even kind of graph. I'm going to graph it kind of not really well. Pretending like this is x to the 4th. We'll come back to this picture in a second. Kind of want to make it a little curvier. Okay. And our a value, well, let's see, what's the thing that's close to 1.95 that's easy to raise to the 4th power? 2. They're going to try and make it easy for you to identify a. A should be something that is easy to plug into whatever your function is. Our derivative here is 4x cubed. F of a is 2 to the 4th, which is 16. F prime of a is 4 times 2 cubed, which is 32. So our linearization is that L of x is f of a plus f prime of a times x minus a. So it's going to be f of a, which is 16, plus f prime of a. So the slope at this point is a really steep slope. It's 32 times x minus a, which is x minus 2. All right. So we're going to use this line to approximate the function value at 1.95. So let me see if I can draw some stuff and make it look kind of smart. So here's x equal to 2. A equal to 2, I guess is what I should say. And here's the tangent line. Did not draw that as well as I wanted to. Sometimes your pictures need to look good, and this is an example where the picture really does need to look good. So let me try and make it look good. Okay, let's try this one more time. See if I can draw a tangent line here. Let's try and draw it like right That's pretty good. Okay. So here is my a equal to 2. And what we're doing is we're saying, well, I'm going to plug in, and let's go over here. Let's say that's x equal to 1.95. And so instead of getting this value here, which would be 1.95 to the 4th, which should be a little bit less than 16, I'm actually going to find this value on my tangent line, which is given by this equation. So this tangent line, it's y equals 16 plus 32 times x minus 2. So by plugging in 1.95, I'm going to get some y value, and it is going to be a little bit smaller. And again, I really want to point out that this here is your dy, is the approximation of the actual function, the change in the function value. Now I'm like looking to make sure I've drawn that correctly. Yeah. Whereas the actual change in this problem would be this amount here. That's your delta y. Okay. So let's see what we get. 1.95 to the 4th is going to be approximately L of 1.95. If we plug that in, it's going to be 16 plus 32 times 1.95 minus 2 is going to be negative 0.05. Negative 0.05 times 32. Here's how I would really do it. I would think of 5 times 32, which I would really do by doing 10 times 32 over 2. 10 times 32 is 320. 320 over 2 is 160. But then I know it's not really 160, nor is it 16. It should be 1.6. That's what 0.05 is times 32. So it's actually going to be 16 minus 1.6, which is going to be 14.4. And that is our approximation of this value. The actual value, use a calculator. I'm just throwing everything on the ground today. Sorry. 1.95 to the 4th is going to be 14.46. So pretty close.
I have a question about the graph.
Yeah.
So I don't really understand the dy and then the inside. I can't really see that part.
Sure. Yeah. So let me draw the picture again. Let me draw it bigger. I know. It's too bad we don't. Yeah. So let me try and make it look better. So let me grab a hot off the press new pen. Probably helpful. Okay. Here's my function. The pen doesn't look very new, although I just took it out of the box. And we are interested in, so again, this is our point A. And I'm going to draw the tangent line, and we're going to pray it looks good. Let's draw right here. Okay, so here's the idea. We are interested in evaluating this function, f of x, at this point A. Or sorry, not at this point A, at some other point close to A. Like x equal to, I'm going to use the same number as 1.95, where A is equal to 2. And so here's the idea. The idea is that I really would like to know, I'm use the right colors here. I would really actually like to know what this value is if I could. right? I would like to know what f of 1.95 is. And we could, but like whatever. But it's easier, right? 1.95 to the fourth power is not the easiest thing to calculate. We could, right? We could do it by hand if we wanted to. It's not fun. But the point is that we can actually use this line. It's always going to be relatively easy to plug in something to a line. Right? You're literally just taking your value of x, multiplying it by the slope, and adding whatever the the coefficient is or the intercept is. So here's what's happening. This amount here, that is your actual change in the function, delta f, or if you prefer, delta y. And it's our actual function value, f of 2 minus f of 1.95. That's the actual change from here to here. I suppose I should actually do I probably should do the subtraction in the opposite order because usually we think about the change happening as we go from left to right. So I should probably really say it's f of 1.95 minus f of 2. And that is the actual change from here to here. But what we're going to do is we're not going to actually calculate that. Instead, we're going to approximate that with the differential, dy. And dy, well, it really is coming from the fact that the derivative dy dx is equal to the derivative. And then we're really just going to kind of treat this like a fraction. And say, okay, well, if the rise over the run is equal to the slope of the tangent line, then the rise is equal to the slope of the tangent line times the run. So this dy here that's your dy. It's almost the same as delta y, but not quite the same. So dy is equal to, in this particular case, f prime of 2, right? That's the slope of this line, times the change in x, which is 0.05. So in this particular case, we already know that f prime of 2 is 32, right? We did it on the other side, times 0.05. So that's going to be, well, and so again, technically fine. Sorry, I'm having a brain. No, I really should. The problem here is that we're going from here to here. So technically the change in y is negative. So I really should say this is a negative 0.05 because we're doing 1.95 minus 2. So it's going to be negative 1.6. That's your dy. And it's approximation of this, which is, well, it's that minus 16, which is about negative 1.54. Which again makes sense. If you look at the picture, the actual change, negative 1.54, is a little bit less than the approximated change, which is negative 1.6. But the thing I kind of there's a few things I want you to take away from this picture. One of them is that we use dy to approximate delta y. The other is that dy is just the slope times dx. Okay, sorry, I thought that was wrote something. Are there other questions about this picture?
So how will we use that to find the Lx equation?
So the L of x, that's excellent question. Thank you. So I'm going to do it up here because I've got some room. So L of x is just the equation of the tangent line. So the way I'm going to find L of x, I'm I'm going to say that L of x is the equation of the tangent line, which is going to be f of a plus f prime of a times x minus a. And I'm finding the tangent line at this point right here. This point being the point 2 comma f of 2, which is 16. So my linearization at this point is going to be f of 2, which is 16, plus f prime of 2, which is 32, all times x minus 2. Now I want to point out that this part here, that is your dy. Right? That's your 16. Sorry, so there's your 16, and then you're adding on dy, which in this case is a negative number, to get the actual approximation of this value here. So dy is the difference, sorry, dy is the approximated difference in the point where it's easy to do things at and the point where you're actually trying to find the value at. Right? So this difference here is your 16 minus your whatever number this is that we haven't found yet. That's given by this, right? It's the slope of your tangent line, 32, times how much you've moved, which is x minus 2, which in this particular example is 1.95 minus 2, which is negative 0.05.
So there's two ways to do it. You can find the change in y or the dy, or you could just plug it into the Lx using, like, deriving the equation, the function.
And so, I mean, the thing is here, so sometimes people talk about, the thing is that people talk about these two things separately, meaning sometimes we talk about the linearization because you want to approximate a function at a particular value. Sometimes we talk about just the differential, which is how much difference there is. So if I could ask this question, I could say, use the linearization here to approximate 1.95 to the fourth, which is what we did, right? We said, oh yeah, 1.95 to the fourth is approximately 16 minus 1.6, which is 14.4. You could also, in a different way, say, if you evaluate this function at 2, how much is it going to change if we move it to the left by 0.05? And in that question, you're not asking for the value, right? The value would be 14.4. You're asking for how much change there would be, which is just approximated by the differential. So there are two pieces here, but they're two pieces of kind of the same thing.
So linearization, when you use that, you find the value, but then for differential, you find the change between those two values?
Well, I want to say the differential approximates the change. But yes, okay. The differential is talking about the change, whereas the linearization, you're usually finding to approximate the actual value.
Okay, thank you.
So, and to kind of get at that question, let me find a question to ask here. Sure. Yeah, I'll take this one. So for a cone, the surface, I should say, the around surface area, or the lateral surface area, is given by, what do we got here? S is equal to pi r times the square root of r squared plus h squared, where this is the height and this is the radius. Use a differential to approximate the change in surface area that results if the radius of the cone of height of 4 inches increases, sorry, let me read that again. Use a differential, so we want to approximate the change in surface area, lateral surface area. If we go from, so if our cone with a height of 4 inches, sorry, a radius of 4 inches, and a height of 3 inches, increases to a height of 3.2 inches. All right, so I could phrase this question a different way. I could have phrased the question as, what's the surface area going to be if we have a height of 3.2 inches instead of a height of 3 inches? And then we would use the linearization to approximate that. And in fact, I'll probably end up doing that as well. So we're starting with a radius of 4 inches and a height of 3 inches. And we're asking what happens to the surface area if this thing just grows a little bit. So now it looks like this. So our cone got a little bit taller. How much did the surface area change? So I'm just asking for the differential here. So the differential, I need to find the derivative. The derivative with respect to what variable? Radius or height? It's a good question. So remember what the derivative means. If I wrote ds dr, this would be asking the rate of change of the surface area with respect to the radius. Or how is the surface area changing as the radius is changing? Is this what I want?
Is it no because the radius is always constant?
Right. In this example, the radius isn't changing. The radius is just 4 inches. The height is what changing. The height is what is changing. So I don't want dsdr because there isn't any. Right? The surface area isn't changing with respect to the radius. The surface area is changing as the height is changing. So I'm going to take the derivative of this expression with respect to h. So that's going to give me, let's see, I have to take the derivative. So r is acting like a constant because it is a constant. R is 4. In fact, if it helps, we might just want to plug in the 4 for r before we even get going on this derivative. So let's say our equation is actually 4 pi times the square root, I'm going to write the 1/2 power of 16 plus h squared. So if you're dealing with problems like this where some things are changing, this is also true for related rates. If some things are changing and other things are constant, it is perfectly fine to actually plug in the values for the things that are constant. So now I'm going to take the derivative. ds dh is equal to the 4 pi constant hangs out. Derivative of stuff to the 1/2 power is 1/2 times our stuff to the negative 1/2 power times the derivative of our stuff, which is going to be, all right, so this is where we have to be a little bit careful here. Oh wait, no, we don't have to be careful here. I was going to do something kind of weird that was going to be wrong. What's the derivative of our stuff? It's just 2h. Part of me wanted to multiply by a dh dt because I was kind of thinking related rates. It's not a related rates problem. There is no dh dt. Okay. So now here's how we find the differential. The differential is super easy to find if you know how to find the derivative. Take that there, put it over there. So here's your differential. It's ds is equal to all this garbage, which I guess we could simplify a little bit. The 2's cancel. You get 4 pi times 16 plus h squared to the negative 1/2 times h times dh. That is your differential. And we can say that the actual change in surface area is approximately the differential evaluated at the easier point. So where is it easier to evaluate it at? When the height is 3 inches or when the height is 3.2 inches? It's going to be the easier number, which is 3. So I plug in 3, I get 4 pi times 16 plus 3 squared to the negative 1/2 power times h, which is 3, times dh, which is the change in h, which is 0.2. So this ends up being, let's see, 16 plus 9 is 25. 25 to the 1/2 power is the square root of 25, which is 5. And then to the negative 1 power is 1/5. So this ends up being 4 pi times 1/5 times 3 times 0.2, which is 0.6. So these numbers don't look great. 0.6 times 4 is 2.4. So I get 2.4 pi over 5. Or I'd probably multiply this by something like, I don't know, 10 and get 24 pi over 50. So that is the approximate, and you can probably reduce that to something else, whatever. That is the approximate change in surface area. When you increase the height of this cone and leave the radius constant from 3 to 3.2. That is not how much surface area there is. But if I wanted to find the actual amount of surface area, I would use the linearization. So again, my function for surface area as a function of height, when the radius is 4 inches constant, we know that that is equal to pi times 4 times 16 plus h squared to the 1/2. And to find the linearization, it's going to be, well, again, we need to, so our function is this, our h value, I really should say, let's call it our a value, because that's what we usually do. Right, our a value is the nice value for h, which is 3. And our derivative, come on, James. We already found the derivative, let me write it again. Our derivative was 4 pi times, let me just write it out. Here. Our derivative was this, which is 4 pi times h times 16 plus h squared to the negative 1/2. Our a value was 3, right? Because we're going from 3 inches to 3.2 inches. So S of A is, plug in 3, you get 4 pi times 16 plus 9 is 25 to the 1/2 is just 5. So when the height is 3 inches, the surface area is 20 pi. And then S prime of A, when I plug in 5 here, I get, when I plug in 3, I get 4 pi times 3 times 25 to the negative 1/2, which is 1/5, which ends up being 12 pi over 5. Okay, so now for my linearization as a function of height is S of A plus S prime of A times x minus a. So I'm using h instead of x. So that's going to be S of A, which is 20 pi, plus S prime of A, which is 12 pi over 5, times h minus a, which is 3. This is my linearization. This part right here is my dy for any value of h. And I'm going to end up plugging in h equal to 3.2. And look, well, in fact, let me say look in just a second. So if we actually approximate the surface area when h is 3.2, it's going to be approximately the linearization at 3.2, which is going to be 20 pi plus 12 pi over 5 times 3.2 minus 3, which is times 0.2. But this part here, that's exactly your ds that we just found. Right, 12 pi over 5 times 0.2 is 2.4 pi over 5, or 24 pi over 50. Right, so that's the connection that I just spent a few minutes trying to really kind of make clear, is that the differential, the difference in the value that we're approximating, is this part of your linearization after you plug in whatever the value is you're plugging in. So the surface area of this cone approximately changed by this value here. And the new surface area of the cone is approximately the old surface area of the cone plus the approximation of how much it changed, which I'm not going to actually find because we don't really care what it is.
I have a question.
Go ahead.
When you're doing the derivative of s of h, you take the original one where it is before you times d of h.
Before I times by what?
dh.
Right. So yeah. So I should say ds is just s prime of h times dh. So s prime of h is just this without the dh. I just didn't write it out again because I was feeling lazy and I'd already done it. But really, I'm just using my derivative rules, right? Taking the derivative of this, which is that's 1/2 times my stuff to the negative 1/2 power times the derivative of my stuff. That's my s prime of h. And then my ds is just this times dh, which is exactly what I'm getting right here. And my ds is just this when I plugged in 3. And when I plug in 3, s prime of 3 is exactly 12 pi over 5. So that's what this is when I plug in 3. And then my ds is just my s prime, 12 pi over 5, times my dh, which is 0.2. In fact, let me write that. Right, so let me use a different color. So this part here, that's my change in h. And this part here, that's my s prime of h. And together, they form devastator. No, they form ds, or devastator, you know. Yeah, gross. Pens. All right. So that's your ds. In fact, to kind of go along with that theme, I know I had some questions here about that. So the other thing people kind of like to ask sometimes are, and I know I saw some of these in the homework for Haas, are questions that might seem really challenging when you first look at them, but they are really not. What do I mean? Well, let's look at an example. Let's say y is equal to, let's make it not super complicated, James. Let's say y is equal to, sorry, now I'm like, let me do natural log of x cubed plus x. I want to find the differential. Find dy. This is not a hard question if you know what they're asking for. It is literally something you already know how to do with an extra step that is dumb. So I know how to find the derivative. I don't know how to write the derivative though. Dy dx is derivative natural log of some stuff is 1 over the stuff times the derivative of stuff, which I might rewrite as 3x squared plus 1 over x cubed plus x. Okay, great. You found the derivative. Here's dy. dy is your derivative times dx. That's it. That's dy. So if anyone ever asks you to find dy, they're really just saying find the derivative and multiply it by dx, or whatever your variable. So right, if y is a function of x, then dy is that derivative times dx. And if you're using a different variable, just change the variable. So if you have something like, I'm going to write something silly like, if s was a function of time, which I guess isn't that silly because we often think of position as a function of time, you could say that ds is equal to the derivative f prime of t times dt, because dt would be the variable we would differentiate with respect to. But that's kind of it when it comes to differentials. There's one other thing I wanted to mention here. Sure. Yeah. So we'll do this question, then we'll take a break. Suppose the radius of a sphere, I'm trying to get rid of all my bad things, is measured with an error, with a percentage error of at most 5%. How is that going to affect the percentage error when we measure the diameter? Or I should say, so what will the percent error be in diameter, the surface area, and the volume? It's a good question. So I guess I should really ask, how do we even express something like having a percentage error of 5% measured in the radius, right? We're actually not given any numbers here. I mean, you could make up numbers if you want. So you could say, okay, the radius is 100 feet, and the error is plus or minus 5 feet on either side. That is one way you could try to tackle this, but I don't really want to have to just make up numbers if I don't have to. And I don't have to. So let's go to the other side. So here's how I often think about this. Percent error is kind of the possible change in your radius, your dr, divided by your actual radius. So if the actual radius were 100 feet, and the possible change in the radius was plus or minus 5 feet, that would be a percent error of 5%, or 0.05. Now there's one small thing I'm missing here for this problem, and that's an absolute value. Because it can actually be above by 5% or below by 5%, so we throw an absolute value in there. So we need to make this kind of work with our other stuff. I know I didn't say that very well, but here's what I mean. So I want to find the percent error in the diameter. I said diameter, right? Circumference. And I know I said diameter. Did I mean circumference? No. Okay, so the diameter is equal to twice the radius. the percent error in the diameter is equal to the change in the diameter divided by the actual diameter. I don't know why. I guess I should put absolute values, so I'm going to do that. Okay. Well, I can differentiate this. If I differentiate this with respect to the radius, the derivative of the diameter with respect to the radius is just going to be 2. So then the differential for the diameter is just 2 times the differential for the radius. So look at what I can do. I can replace this with, well, dd is 2dr, and d is 2r. The 2's cancel. I get dr over r, which you already know is 5%. So that's kind of interesting. If you measure the radius accurately to 5%, you've also measured the diameter accurately to 5%. Because essentially whatever you're off by for the radius, you're going to be off by that much, the same amount for the diameter, but because the diameter depends linearly on the radius, it's not going to change the percent error you've got, right? Your diameter is going to be twice as big, error is also going to be twice as big. So, for example, with using real numbers, if my radius was, say, 100 feet, and my error in measurement was, say, let's say it wasn't actually 5%, let's say it was like 3 feet, and I measured it, well then, when I measure the diameter should be 200 feet, but the error is going to be 6 feet, so it's still going to be the same amount of percentage error. This is not true when we go higher dimensions. Let's look at surface area. So the equation for surface area of a sphere is 4 pi r squared. And I'm trying to find the percent error in the surface area, which is given by how much I'm off by for the surface area divided by the surface area in absolute value. Okay, so I need to find ds. I know how to find ds, I'm just taking the differential. So s, well, so there's s, so ds dr, derivative of 4 pi r squared is 8 pi r. And then I'm going to multiply both sides by d. I'm not really multiplying by the dr over. So ds is equal to 8 pi r dr. Okay, so check this out. I've always thought this was kind of slick. ds is that 8 pi r dr. S is 4 pi r squared. What can I cancel? A lot of things. 8 over 4 cancels and gives me a 2. Pi over pi, r over r. So I'm left with 2 dr over r. And I can bring the 2 out of the absolute value. You can get 2 times the absolute value of dr over r, which is equal to 2 times, well, dr over r is 0.05, so it's 2 times 0.05, which is 0.10. So if there's a 5% error in measuring the radius, there's going to be a 10% error in measuring the surface area. Any guesses for what our error is going to be in measuring the volume? Oh man, that's a lot of cracks. Yeah, you're right, Helena. It is going to be 15%. So basically, every dimension you add on to your, or every dimension you increase by, adds on to your, or multiplies your error by that amount of increase. So if we go from 1 to 2 dimensions, it multiplies by 2. If we go from 1 to 3 dimensions, it multiplies by 3. And then exactly because, so we have, we're finding the differential of volume divided by the volume. And we know that the volume of a sphere is 4/3 pi r cubed. the derivative of that, this is 4 pi r squared, right? The 3's cancel. So dv is equal to 4 pi r squared dr. And we end up getting 4 pi r squared dr over 4/3 pi r cubed. 4 cancels, pi's cancel, r squared cancels, r squared. Divided by 1/3 is like multiplying by 3. So we end up with 3 times dr over r. But dr over r was still 0.05. So we get 15% error. Okay. The extreme value theorem says the following. Basically, the extreme value theorem says if you're, well, no, it's not basically, it's literally what I'm about to say. So if your function f is continuous on a closed interval, say a to b, then f attains an absolute maximum and an absolute minimum. Within the interval. Furthermore, the absolute max slash min occur either at an endpoint, so A or B, or a critical point. And a critical point is a place where the derivative is either 0 or undefined. And yes, the function can be continuous on the interval and still have a derivative that's undefined. We know functions like this, like the absolute value function, which is definitely continuous, but not differential everywhere. So a couple of just pictures to kind of see what we mean. If you have a function that isn't on a closed interval, so like maybe it doesn't ever stop, there's something like this that just keeps going, you don't actually have a maximum or minimum, right? Because it keeps getting larger and smaller. So you have to have the closed interval to guarantee you have an absolute max and absolute min. But you could have something that maybe look like this. Maybe it starts here. That's actually not what I meant to draw. Oh well, so I drew it wrong, that's fine. So I have an absolute minimum right here, right? This is the smallest y value that this function has. And up here we have an absolute maximum. That's the largest. So sometimes your absolute min and your max occur at the endpoints. Sometimes they occur in between. Like you could have something that looked more like this. Where again, this is your A, this is your B. Right, here's our absolute minimum again. And I abbreviate absolute with ABS. But here, there's your absolute maximum. And if it's not at an endpoint, it has to be at a critical point where the derivative, aka the slope of the tangent line, is 0. They can also both occur in between. Let me go to the other side of this. Sure. So you can also have something funky like maybe your function is some sort of absolute value thing. Maybe it looks like this. Maybe it's a piecewise function. Maybe someone came up with something crazy. Said, I'm going to make it like a parabola for a little while, and then I'm going to make it an absolute value function for a little while. And then I can see that I have an absolute minimum right there. It's not an endpoint. It is where the derivative is undefined. because it's a corner or a cusp. And then it looks like this is probably the biggest point. So extreme value theorem just says if you've got a continuous function on a closed interval, you have to get an absolute minimum and an absolute maximum within the interval. It is possible to have more than one. Sometimes you can get two absolute maximums if they're the same y value. We'll see an example of that. Yeah, I'll show you an example of that. Well, let's go ahead and look at some actual examples with real functions, not just drawing pictures willy-nilly. I mean, I don't have a problem with willy-nilly, but you know. Okay. So, yeah, I say so like so many times. My wife is telling me like, you say so a lot. I'm like, I know. One day I said so a lot, and then started saying even more because it's like so. So, let's look at this function. F of x equals to x over x squared plus 1 on the interval from 0 to 2. And I want to find where it has an absolute maximum and an absolute minimum. So I'm going to find the critical values. So to find the critical values, I'm going to find the places where the derivative is 0 or undefined. So I'm going to take my derivative. I'm going to use the quotient rule. It's going to be the bottom times the derivative of the top, which is 1. So I'm not going to write that down. Minus the top times the derivative of the bottom, which is 2x, all over the denominator squared. Chair move. And then we have to simplify, right? Because we're trying to figure out where this is equal to 0 or undefined. So I get x squared plus 1 minus 2x squared all over x squared plus 1 quantity squared. I'm not going to multiply at the bottom. I would also point out that this is never going to be undefined because the denominator is always greater than or equal to 1. So simplifying the top, x squared minus 2x squared is negative x squared. So the numerator is 1 minus x squared. The denominator is x squared plus 1 squared. And I'm going to factor the top. It's going to be 1 minus x times 1 plus x over x squared plus 1 squared. So what are my solutions to this? My solutions are x equal to 1 and x equal to negative 1. So my critical values are x equal to 1 and x equals to negative 1. Okay. Should I make a mistake? Yeah, I'm going to make a mistake. Okay. So here's how we figure out where we have an absolute maximum and where we have an absolute minimum. We just plug in these points to the function and see what's the biggest. So I'm going to look at f of 0. I'm going to look at f of 2. Those are my endpoints. I'm also going to look at f of 1 and f of negative 1. So f of 0 is 0 over 0 plus 1, which is 0. F of 2 is 2 over 4 plus 1, which is 2/5. F of 1 is 1 over 1 plus 1, which is 1/2. And f of negative 1 is negative 1 over 1 plus 1, which is negative 1/2. Okay. Of these numbers, which one is the biggest? It's either 2/5 or 1/2. Which one is it? Thanks. Yeah. All right. So here's where the mistake is going to come into play. Of the numbers I've listed, which one is the smallest? It's okay to say what you know is the wrong answer. And negative 1/2 is the smallest one. But that's not the right answer because my interval was actually from 0 to 2, which means that even though negative 1 is a critical value, it's not a critical value that's in my interval that I'm being asked about. So I shouldn't have even considered that one. But it's an easy mistake to make, right? So you say like, oh yeah, negative 1's critical value, plug it in. Oh, it's the smallest one. So it would have been, if we weren't paying attention, we might have said, this is the absolute minimum. But it's not. Not on the interval we're talking about. The absolute minimum is going to be the smallest thing in the interval we're talking about, which is going to be at 0. So, and I don't know how your teacher wants you to phrase your answers, but here's what I would say. we have an absolute minimum at x equals 0 with a value of f of 0 equal to 0. Or if you want to write less, which I want to write less, you can say you have an absolute minimum at 0, 0. We have an absolute maximum at x equal to 1 with a value of 1/2. So we typically talk about the extrema occurring at the x place with a value of the y value. So this absolute minimum is at 0, 0. This absolute maximum is at 1/2, 1 comma 1/2. Where it's really at x equals 1 with the value of y equals 1/2. Really at x equals 0 with the value of y equals 0.
I have a question.
Go ahead.
So critical point is what values when x is 0?
Not when x is 0, when the something else is 0.
When y is 0?
When y is 0.
The derivative is 0?
Yes. Because, right, so if I was looking at this picture, I would say, oh, well, I definitely have a maximum right here. Is it an absolute maximum? No, it's not an absolute maximum. Because this point over here happens to be bigger. But that's a critical point, and we need to consider when we're looking for where we might have an absolute maximum or absolute minimum. But yeah, so I will say the way we find critical points is we find where the derivative is 0 or where the derivative is undefined. Right.
That's why we instead of while doing x equals 1 and x equals -1, we also did x equals 0 and 2 to find those values.
0, 2 we did because of the endpoints.
Okay.
So when you're talking about the extreme value theorem, a function can either have an absolute maximum or minimum at a critical point where the derivative is 0 or undefined, like in the picture I just erased. So like, right, so we can definitely have, right, we can have an absolute maximum here, critical point, derivative is 0. We can have an absolute minimum here, critical point, slope of the tangent line is 0. But you could also have something more like this, where, oh yeah, at this point here, you definitely have an absolute maximum at the critical point where the derivative is 0, but we have an absolute minimum not at the critical point, but at an endpoint. So for absolute extrema on a closed interval, your options for where the absolute extrema can occur are either at critical points or at endpoints. And then we check to see which one it is just by seeing which is the biggest and which is the smallest by plugging back into the original function.
If you go back to the other graph,
Oh,
the
sorry.
the absolute maximum was at the endpoint.
That is not correct. The absolute maximum. So actually, let me draw this graph, and I'll show you. So x over x squared plus 1 looks like, let's see. So when in fact, let me use these points. When I plug in 0, I get 0, 0, 1, 1/2, 2, 2/5. So I get 0, 0, I get 1, 1/2, and I get 2, 2/5, which is a little bit smaller. So this function looks, and it is an odd function actually, I know. So it looks like this. But I'm only specifically looking at the section from x equals 0 to 2. So I'm only looking at this section right here. And in that section, the maximum is right there at 1, when x equals 1, right? That's the biggest y value of all the y values in the blue section. And the minimum is over there at 0. That's the smallest y value for all the y values in this section.
Okay.
Let's look at another example. Let's look at, say, g of x equal to x cubed minus 6x squared on the interval from -1 to 7. So again, I'm going to do the same thing I did before. I'm going to find the critical points. I'm going to find or use the endpoints. I'm going to take my critical points and my endpoints and plug them into the original function to see what's the biggest and what's the smallest. And again, I suppose I should write the question, right? Find the absolute max and min for this function. So the derivative here is 3x squared minus 12x. We'll set that equal to 0. I'm also going to think about where it's undefined, but I know that this function isn't undefined because it's just a polynomial. So factor, I get 3x times x minus 4. So my critical values are x equal to 0 and x equal to 4. So then, and now I should point out, both of those critical values are in the interval. So I'm going to use both of them. So then I'm just going to take all my critical values and plug them into the, I should say all my critical values and my endpoints and plug them into the original function. So I'm going to find g of 0, which is easy. G of 0 is 0. I'm going to find g of 4, which I'll talk about in a second. Also going to find g of -1 and g of 7. And here's the thing. I'd really rather not plug it into the function as is. 4 cubed, fine, 64, but 6 times 4 squared is more math than I want to do. It's even harder when it's 7, right? 7 cubed is 6 times 7 squared. No. It's going to make your life easier when you're plugging things into the original function if you can simplify or factor the original function. I'm going to factor out the x squared and write it as x squared times x minus 6. Because now plugging in 4 is easy. Plugging in 4, I get 4 squared times 4 minus 6, which is 16 times -2, which is -32. G of -1 is easy anyway, you slice it. But I get -1 squared, which is 1, times -1 minus 6, which is 1 times -7, which is -7. And g of 7, much easier here. It's going to be 7 squared, which is 49, times 7 minus 6, which is 1. 4 minus 1 is 49. Okay, what's the biggest? That one. What's the smallest? That one. So the way I phrase the question, I could say I have a maximum value of 49 at x equal to 7. I have a minimum value of -32 at x equal to 4. Let's look at one more like this. Well, similar, I should say. Actually, before I look at one more like this, let me just show you what the graph of this looks like so you can kind of see. Sure. So this function, x cubed minus 6x squared, or x squared times x minus 6, has x intercepts at 0 and 6, and looks kind of like this. And here's the minimum at 4, -32. Here's the point, maybe -1, -7. Here's 0, 0. And here's 7, 49. So from here to here, we can see that, oh yeah, of course, this is the maximum, right? That point is higher up than any of the other points. And of course, this is the minimum. That point is lower than any of the other points. I will also mention, because we're going to start talking about this sooner than later, this point here, although it's not an absolute maximum, right? It's not the biggest thing we have. It is a relative or local maximum. because that y value there is larger than all the y values that are next to it. So that's a local maximum. In the same sort of way, this point here is a local or relative minimum. This point here is not a relative maximum. It is not bigger than all the things on either side of it, because the things that are on the other side, which we're not looking at for this interval, are definitely bigger than.
So there are local maximums and relative maximums and minimums, and then there's...
And those are the same things, right? Local or relative means the same thing.
Oh, do they have any significance?
Yeah, very much. Yeah, they have great significance. So the thing about local maxes and local mins, or relative maxes and relative mins, again, we use the word local because you're saying in this locality, right? This is the biggest thing, or in this locality, this is the small thing. We use the word relative. We're saying this point relative to the points around it is the biggest thing. This point relative to the points around it is the smallest thing. And certainly one of the things we do with local extrema is we use them to graph things, right? So we're working towards graphing these functions nicely. And one of the things we're going to do is we're going to actually include the points where you have a relative extrema, whether it's a minimum or a maximum, even if it's not the absolute maximum or the absolute minimum. And they also definitely come up when we talk about optimizing functions. We're trying to see what makes this thing the biggest or the smallest on some domain. We usually are looking for the relative maximum and minimum. Let's look at one more example of absolute extrema. So let's look at this. Let's say we have the function f of x equal to x to the 2/5. 2/5, yeah. On the interval from -1 to 32. And I want to find where the absolute max and absolute min occur. And again, I know they have to because x to the 2/5 is a continuous function on that interval. There are no breaks. So I'm going to find the derivative. F prime of x is 2/5 x to the -3/5. All right, I'm going to ask kind of a trick question. Where is this equal to 0? And I will remind you, this is kind of a trick question. Everyone's like, I don't want to say anything now. It's a trick question. Okay. The trick here. So thank you, William. You went for the trick. I appreciate your bravery. 0 is still going to be an answer, even though it's not the answer to this question. So this expression is actually never equal to 0. Because if you plug in 0 for x, 0 to the -3/5 isn't 0, it's undefined. It's easier to see if we rewrite it as f prime of x equal to 2/5 x to the 3/5. Now I think everyone is a little more confident saying, oh yeah, look, if I plug in 0, 0 cubed is 0, the 5th root of 0 is 0, 5 times 0 is 0, and dividing by 0 is undefined. So f prime of 0 is undefined. However, that still means it's a critical point, right? We want to find places where the derivative is either 0 or undefined. So usually, even if you make this kind of error of thinking it gives you 0, you're usually pretty safe. But just be aware, right? 0 to a negative power is undefined. It's not equal to 0. So our critical point, not critical value, is x equal to 0. Critical point would be the x and y coordinate, right? If I say critical point, it would be 0, 0. The critical value is x equal to 0. So now we're going to check all of our, so that's our only critical value, right? There's only one place where this derivative is undefined and it happens to be x is 0. So, now, sure. Let's go ahead and evaluate this at all of our points. So I'm going to have f of 0. 0 to the 2/5 power is just 0. Right? The original function should still be defined there, even though the derivative is not. F of -1. What's -1 to the 2/5 power? Well, you can do either one first. -1 squared is 1, and the 5th root of 1 is still 1. Or you can do the 5th root of -1 is -1, and then -1 squared is +1. All right, here's a harder question to answer. What is, sorry, that's a positive 32. What is 32 to the 2/5 power? Yeah, it is 4. Yeah, and definitely you don't want to do the squaring first, right? You don't want to do 32 squared and then do the 5th root of that. You want to do the 5th root of 32, which is 2, and then 2 squared, which is 4. You could do it the other way, but it's silly. So that one's the biggest. That one's the smallest.
Wait, how do you find 32 to the 2/5 power?
Sure. So 32 to the 2/5, the way I think about it is you do 32 to the 1/5 squared. And 32 to the 1/5 is asking the question, what number do you multiply by itself 5 times to get 32? And the answer to that question is 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5th is 32. So 32 to the 1/5 is 2. And then 2 squared is 4.
So you could bring out the 2 in the 1/5, or in the 2/5.
Right, because what I'm exploiting here is the fact that when you have a power to a power, you would multiply the powers. So if I go backwards, right, 32 to the 1/5 to the second is 32 to the 1/5 times 2, which is 2/5. So yeah, I'm really breaking apart 2/5 as 32 to the 2/5 is really 32 to the 1/5 times 2, which is really 32 to the 1/5 to the second.
Okay,
So here's what's going on. X to the 2/5. Well, we know some values, right? We know that if we plug in -1, we get 1. We know that if we plug in 0, we get 0. And we know that if we plug in 32, we get 2. Let's pretend 32 is out here. And we know that at 0, the derivative is undefined, which means we have like a pointy point. So it looks like this. Like that. So, oh yeah. There's my biggest value, my absolute maximum at 32, 2. Here's my absolute minimum at 0, 0. And here's my other critical point, or not critical point, but endpoint at -1, 1. Okay, so when you're asked to find the absolute max or absolute min, this is the process. Find the critical points by taking the derivative and seeing where it's 0 or undefined. Plug in your critical points and your endpoints to the original function to see what's the biggest and what's the smallest. So, yeah. Have you guys started talking about the mean value theorem yet? A couple yeses, great. Then we should start talking about it. So, here's kind of a motivating question. If you drive over a 1-mile bridge 1 minute. And the speed limit is 55 miles per hour. Did you break the law? I mean, right, speeding, okay, who really cares? But did you exceed the speed limit? So let's phrase it that way. Well, it's a good question. That was black. That's so terrible. So I've noticed, and I'll point out, right? I didn't say that I was driving the same speed the whole time. I'm just saying I crossed that bridge in 1 minute. So maybe I was driving super fast in the beginning and then slowed down. Maybe I was driving slow and sped up. But did I go over 55 miles an hour? Well, let's take a look. Well, let's see. I went 1 mile in 1 minute. Well, okay. Let's change that to miles per hour. I went 1 mile in 1 minute, which is 1/60th of an hour. If I flip and multiply, or multiply the top and bottom by 60, I went 60 miles per hour. So at least my average speed was 60 miles per hour. Did I drive 60 miles per hour the whole time? No. Did I have to be driving 60 miles per hour at least at one moment? Yes, I did. So I broke the law. I get a ticket, go to jail, not pass go. So the idea with the mean value theorem, which is what we're kind of getting at here, is that if your average rate of change is some value, the mean value theorem says that your instantaneous rate of change had to also be that value, at least at one moment. Let me draw a picture to kind of help explain this. So let's say it's still the same question. So on my x-axis, we'll call the t-axis time, and on the y-axis, we'll say position or distance. 1 mile, 1 minute, which is 1/60th of an hour. So I know that as time goes on, my position is going to get to be exactly 1 mile. So I'm going to be up at this point. And maybe I start off kind of fast, and then I slow down, and then maybe I speed up again, and then slow down, and then, okay, I get there. And I didn't like drive like stopping and starting, although I did kind of, I almost stopped there. I was going real slow for a minute. So the question is, does my instantaneous rate of change ever have to equal my average rate of change? The answer is, well, certainly yes. So my average rate of change is just equal to the slope of the line that connects the endpoints. Change in y over change in x. Or change in distance over change in time, which we already calculated to be 60 miles per hour. But it's really just the slope of that line. So let me ask everybody, is there a place on my graph where the instantaneous rate of change, that's the derivative, also known as the slope of the tangent line? Sorry, I don't know why I'm whispering. My wife's not here. I'm whispering because it's funny. Because the point is, of course you can see that, yes, there's a couple places where my slope is definitely the same as the slope of this, maybe right about there. Looks like the slope of my tangent line. Whoa, wow, good job, James. Come on. Come on with the drawing. Right, maybe about right there. It certainly seems that the slope of the tangent line is the same as the slope of that secant line. The M here and M here are the same. So if there's a place or the tangent line is parallel to the secant line, then yes, you're going to have that happen. And the thing is, unless there's some sort of weird discontinuity or lack of differentiability, this always happens. You can't not get there, even if you drive kind of weirdly, right? Let's say instead, and we know we have to get up to that point there, right? Even if we did something like this, there we go, right? All right, I was going real fast, then I turned around and went backwards, then I, right? Now I know, like, right, so like, right, I slowed down, I stopped my forward progress, I threw it in reverse, went backwards, threw it back and forwards, went up, right? But even in this example, there's actually a couple places where my speed, right, had to be maybe like right about there, right? My speed's like 60 miles per hour right there, and maybe right about there. And there's a couple places where my tangent line has the same slope as my secant line. And that's what the mean value theorem guarantees. That if you're on a closed interval and your function, by representing, in this case, your position versus time, where your function is continuous and differentiable, then there has to be at least one place where the derivative, aka the slope of the tangent line, is equal to the slope connecting the endpoints, or the average rate of change. So the way people often phrase this is, the mean value theorem says that the average rate of change, there's at least, I should say, the mean value theorem says there's at least one place in an interval where the instantaneous rate of change is equal to the average rate of change. It also makes sense, right, that if you average 60 miles per hour, there was at least one moment where you had to actually be driving 60 miles per hour. If you were always going less than 60 miles per hour, your average wouldn't be 60 miles per hour. If you're always driving more than 60 miles per hour, your average wouldn't be 60 miles per hour. So to have had an average that was 60 miles per hour, you had to go from below to above or above to below, at least at one moment. Or just driven 60 the whole time. But no matter what, you had to have that value at least once. So here's how the mean value theorem is typically stated. Come on, Patton, work. So the mean value theorem, which we often abbreviate as the MVT, just like we abbreviate the intermediate value theorem as the IVT. The mean value theorem says the following. If your function, so it has to be continuous and differential, right? If it's not continuous, you could have some weird jump, like, so I could point out, like, maybe if I was pretending like my function wasn't, like, if it was possible to drive this way, maybe I was going, that's not a good, now I picture, I'm like going to try and draw a picture. Right? Maybe I did something like this. Maybe I was going like this. I'm like trying to draw it now, and now I can't think of how to like make it work right. I'll do that in a second. So sorry. So fx is continuous on the closed interval and differentiable. It actually doesn't have to be differentiable at the endpoints, although it usually is. But we don't need differential at the endpoints. It will only be differentiable on the open interval from A to B. If those two things are true, then there exists at least one, although there could be more, at least one point, which we usually call C, such that, I'm going to say the words again before I write the formula. The words are that the derivative at C equals the slope of the line connecting the endpoints. The way I write that is the derivative at C equals the slope of the line connecting the endpoints. Right? If this point here is B comma f of B, and this point here is a comma f of a, then the slope of the green line is the difference in the y's, f of b minus f of a, over the difference in the x's, b minus a. And what the theorem says, and I forgot one important small thing, which I'll fix in a second. The theorem says there has to be a number c, at least one, but maybe more, where the derivative at the point c is equal to the slope of that line connecting the points, the endpoints. Now, there was one thing. There's at least one point c between a and b, such that this is true. F prime of c equals f of b minus f of a over b minus a. And again, all this is really saying is that if you've got some function over some interval, there is at least one point in between the interval, the endpoints, where the instantaneous rate of change, or the slope of the tangent line, is equal to the average rate of change, or the slope of the line connecting the endpoints. Now, the bummer, kind of, about the mean value theorem is that it's super important, but there's not a lot, although maybe there are in web work, but to my knowledge, there's not a lot of great questions we can ask to kind of get at the heart of really understanding the mean value theorem. The most common type of question that we typically ask are, for a certain function, find the values guaranteed by the mean value theorem. So let me give you an example. For the function f of x equal to x cubed minus x squared on the interval from 0 to 4, find all values of c guaranteed by the mean value theorem. Okay, so here's what this is really saying. We've got this function, and I don't know exactly what it looks like. That's not true. I pretty much know what it looks like. It looks like x squared times x minus 1. It's got a y-intercept at 0, and it's got a, x-intercept at 0 and x-intercept at 1. It kind of looks like this. Well, it's kind of, I don't really care that much. So over here, right, I've got the point 0, 0, and I've got the point 4, comma, if I plug in 4, f of 4 is going to be 64 minus 16, which is 48. And so here's what I'm really asking for. I'm asking for what we're being asked to find every value of c such that the derivative at c is equal to the slope of that line connecting the endpoints. So we want to find c such that f prime of c equals f of 4 minus f of 0 all over 4 minus 0. That's what we're being asked to do. Now, we know there has to be one or more, but at least one, because the function is continuous and differentiable. And we know it's continuous and differentiable because it's a polynomial. And polynomials are continuous and differentiable everywhere. So let's see, we're trying to find a c so that f prime of c is equal to, let's see, f of 4 is, well, we already said it's 48, minus f of 0 over 4 minus 0, so that's going to be 12. So we're trying to find where the derivative is equal to 12. Okay, that's pretty attainable. So f prime of x is 3x squared minus 2x, and we're going to set that equal to 12. And we're going to try and solve this. So the only way I can do this is by bringing the 12 over and say 3x squared minus 2x minus 12 equals 0. And I'm hoping it factors, but I really don't think it does. Maybe it does. You know what? I'm not going to try that hard. Instead, I'm just going to use the, not the Pythagorean theorem, the quadratic formula. So let's see. So I'm solving 3x squared minus 2x minus 12 equals 0. So my solutions are negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, where a is 3, not a. So let's see, I get 2 plus or minus the square root of 4 minus 12 times minus 12 is plus 12 squared, which is 144. This is definitely not going to turn out nice. Good thing I didn't spend too much time trying to factor it. All over 6. So this is going to be 2 plus or minus the square root of 148 all over 6. I might be able to simplify that a little bit. I really don't care to. Now, here's the question. So, in fact, yeah, this is about, so I know that this is pretty close to 12. Not exactly, but close enough. So this is kind of like 2 plus or minus 12 all over 6, which looks like 2 plus 12, 14 over 6, and 2 minus 12, negative 10 over 6. So let me ask you guys, are these my answers? Are those the values of C that are guaranteed by the mean value theorem? It said there was at least one, but is it true that both of those are guaranteed? Well, to answer that question, we should go back and look at our interval. The interval was from 0 to 4, and the mean value theorem says that there is at least one value C between A and B. So the f prime of C is equal to f of B minus f of A over B minus A. So I should have said find C between 0 and 4. If there are multiple answers between 0 and 4, then we should say them. But in this case, there are not. There is only one answer that's between 0 and 4, and it's the one that's approximately that. So our actual only answer here, the only value of C guaranteed by the mean value theorem, is the one that is positive, 2 plus the square root of 148 over 6. So be careful with that, because people will try to ask you questions where you get multiple values of C, and not all of them are actually in the interval that we care about. So your answers, when you're finding the values guaranteed by the mean value theorem, have to be in the interval that you're being asked about.